Okay, good morning everybody. My name is Cody Knowles and we're Team 7. You may recall from our project that we're using a microcontroller to control a motor, which makes its decisions based on feedback from a pressure sensor. So for this reason we're very interested in different types of sensors and how they interface with microcontrollers. So let's start our discussion by talking about a few different types of sensors. Sensors can be classified into two main groups, first of which being passive sensors. These sensors are defined in that they don't require any sort of external power, and they actually generate their own electrical signals based directly on the sensing parameter input. This is typically accomplished by taking advantage of certain material properties, and a good example of this is found in what's called piezoelectric material. Piezoelectric material is a specific type of material that contains dipoles that are oriented in a very specific asymmetrical pattern, such as shown over here. If you imagine these green balls to be dipoles. So while at rest, these dipoles remain at charge equilibrium. However, when the material goes under strain, and these dipoles are actually physically forced to move, dipole moments are created, and this polarizes the material itself, creating a potential difference from top to bottom, say. And as you can see from this little animation we have here, when the material is squeezed, the voltmeter reads higher voltages. And so using a sensor like this, you could accomplish measurements such as, say, force being applied to a wall, or perhaps tension in a cable, things of that sort. Another good example of a passive sensor is what's called a photodiode. These are like regular diodes in that they're PN junctions that only allow current to flow in one direction. However, it's not voltage that turns them on, but rather photon energy or light. The way they work is this. If you look at this little diagram, the material is created such that when incoming light or photon energy enters the material, it has enough energy to actually kick out an electron, causing electrons to flow one way, holes to flow the other. Now, as electrical engineers, we know this to be a current, and so that we can measure this, and thus we have our sensing is achieved. And this is used, things such as night lights. When the lights go off, the night light comes on with the diode turning on and off. Also, if you recall back to ECE480, there was a lab that we all did that involved turning on and off a fan by putting your hand over a photodiode, and this was supposed to simulate, say, smoke in the room. Smoke filled the room, the diode would turn on, the fan would turn on, blow the smoke out of the way. You can also use this type of sensor to accomplish motion sensing. Say if you shine a constant laser into the eye of the diode, and say something jumps in front of it and cuts the laser's beam, then your sensor will know something's passed in front of your sensor, and that's that. So why would we want to use this type of sensor? Because they don't require any sort of external power, they tend to be very cheap, both cost and actually power, because when they're just sitting there waiting for an input, no current's flowing, there's no power being consumed. By the same token, because they don't require any external circuitry, they're very small, tend to be much simpler circuits, and very easy to implement. The disadvantage of this, however, is that they tend to be less accurate than active sensors. And the main reason for this is because you're relying on material property to accomplish your sensing. If similar material from different origin is asked to measure the same thing, they might read a slight discrepancy in, say, the magnitude of whatever electrical signal. Say if two factories produce the same type of sensing material, but manufacture them in slightly different ways, you might see these types of discrepancies based solely on slight differences in the material itself.
My name is Casey Davidson, and today I will be discussing active sensors with you. The key distinction that makes a sensor active is that active sensors require some form of external excitation. And what this means is that in your design, you are required to include some form of external active circuitry, allowing the sensor to produce its electrical output. Now, you can have either AC or DC excitation, both of which have their advantages and disadvantages. DC excitation, the advantages of that is that it's low cost and its simplicity of its implementation. The drawback to DC excitation is that when viewing the outputs, it becomes difficult to distinguish between the actual output signal and the errors that are produced due to the DC offset and thermocoupling effects. These DC offsets are actually not fixed. They fluctuate due to what's known as temperature drift. And AC offset, although it comes at a much higher cost, is actually capable of eliminating these errors, as well as producing the output signal of the sensor at much lower voltages and currents. Once it's established that you're using AC or DC excitation, the sensor then requires either a form of constant voltage excitation or constant current excitation. Constant voltage excitation is typically used in data acquisition applications such as strain gauges or pressure sensors, whereas constant current excitation is more typically used in some form of resistive sensor such as a thermistor. And additionally, it also increases noise immunity, making it ideal for industrial applications. And additionally, another nice thing is that active sensors are actually capable of having some form of onboard amplification, meaning that you can eliminate the use of external circuitry to amplify or scale down your output signal. There's actually many different kinds of active sensors available on the market. One I'd like to share with you is known as a thermistor, which I mentioned earlier. A thermistor is actually very similar to your standard resistor, except that due to its chemical makeup, the resistance across the thermistor changes drastically due to changes in temperature. Now, to determine the temperature in, say, a room, by calculating the resistance across the thermistor, again, means that you will require some form of external excitation to calculate this. Additionally, another type of active sensor I'd like to share is known as a strain gauge. This particular strain gauge depicted here is what's known as a cantilever strain gauge, meaning it is fixed on one end while a force is applied to the other end. Now, what it utilizes is something known as bridge circuitry, where in this particular case, there's 4 resistive elements, 2 of which are on top and 2 are on bottom, and they're arranged in what is known as a Wheatstone bridge. When the strain gauge is in equilibrium, meaning there's no force being applied, this bridge is actually perfectly balanced and there will be no output voltage. However, once a force is applied in either direction, the resistive elements will change in value, causing the bridge to become unbalanced, therefore producing an output voltage that can be directly correlated to force. But in order for the sensor to output its electronic voltage, it requires some form of constant voltage excitation, as you can see from the BCC diagram. So the advantages of active sensors is that active sensors are actually capable of voltage and temperature compensation, meaning that it can be used in a variety of different environments, increasing the versatility and different uses of active sensors. Additionally, as I mentioned before, active sensors are actually capable of scaling their own outputs internally, meaning you can then therefore eliminate things such as including amplifiers and other circuitry to connect up to your sensor, making it much simpler in your design. However, active sensors tend to be more expensive than passive sensors, and they will also increase the total cost and size of your design because you need these additional active circuitry elements in order for this sensor to operate.
Hi, I'm Tom Gordon. I'm going to be talking about how you connect to this microcontroller you chose, as well as some other considerations you may need to take into account when you're choosing a sensor. Like Casey said, if you use an active sensor, you may need some sort of external circuitry. In our case, it's more of a biomedical application, so we tend to use a type of external filter or external amplifier known as an instrumentation amplifier. So you can see there's an input stage and a gain stage. This type of amplifier allows for high noise immunity. It rejects all common mode noise. It has a high input impedance, and it also offers very low drift in your signal. We use this type of amplifier to step up these signals from the lab tests or patients, which tend to be in microvolts or millivolts. We want to get these into a range where we can actually view them and do something with them. Another form of external circuitry we may need is some sort of external filter. We've all had enough classes to know what an external filter does and how it needs to be implemented, as well as some of the power constraints it may have and all the amplifiers you will be using and filtering features. The other thing is an external resistance for your power supply. If you chose a power supply that supplies a constant, let's say 5 amp current, you might need a resistor or two to step it down so your sensors don't fry or burn out during lab tests or other forms of testing you may need. Also, final thing, when you connect to your microcontroller is a slew rate. So the picture on the right or the left here shows the slew rate of a signal as opposed to a square wave. Square wave is in red. That's the ideal signal that we are trying to generate. The slew rate is slightly skewed a little bit. This is because the slew rate of any type of amplifier or device that you're going to implement in an external circuitry has some time where the whole voltage in the circuit cannot change. It's because voltage can't change instantly all the time. You can see it's voltage over seconds or milliseconds, just depending on the type of scaling you want to use. And this can be on the order of thousands of volts to hundreds of volts. And slew rate also introduces many nonlinearities into your signal, just because of this shift we have as opposed to the reference signal here. And these nonlinearities may also introduce some noise, so you may need another external amplifier, or not amplifier, an external filter to get rid of this noise. Another consideration you must take when you're choosing your sensor is A to D conversion. This graph on the left here shows two signals, one an analog signal of voltage versus time, another one of the same signal but digitized. There's sampling rate, where you must choose a rate that is not too high or too low. If you choose a rate that's too high, you may introduce some sort of quantization noise, which will also impede the clarity of your signal, as well as make it economically not viable. The file size may be too big, the bit stream may be too long, so you could have other errors that are introduced unintentionally if you choose your sampling rate too high. If you choose your sampling rate too low, your quantization levels may jump drastically, and your signal may not be mimicked very well. So we tend to use a sampling rate known as a Nyquist rate. It's the most robust rate we've come up with, so it works very well, and it allows for very good data recovery when we're trying to digitize a signal. Another reason why we try to digitize signals is because the microcontroller reads these signals, and the very well-defined quantization levels help it make its decisions when it comes to a feedback loop or that type of thing. And the last reason why we use digital signals is they tend to travel very well through the hardware, and it's also picked up really well by the microcontroller when it comes through the hardware. Another issue is your clock speed of your microcontroller. Again, microcontrollers are made to withstand a lot of different multitasking capabilities, and the clock speeds are adjusted for that. So your clock speed of a microcontroller may or may not be your biggest concern, but it's something you have to consider. So you have a microcontroller that can keep a timer going, keep your output being outputted, and make sure that all your comparisons from your pressure sensor, in our case, are being taken in real time as opposed to a sort of lag, which may lead to unintended results when you get into the lab environment.